We're going to be the next ones to tell you about the Bayesian optimization. This is an optimization algorithm which uses probability theory and Gaussian processes to optimize black box functions. So the use cases are quite simple. This method is pretty convenient in such cases. When the source function is really expensive to evaluate, or the function is continuous but lacks special structure, for example, concavity.
Or we have a simple form of a set A. In this example, it's constraints.
Box constraints.
So the next is when we cannot evaluate the derivative, and the last is we know about noise in our data. So main idea it's about we use Gaussian process, Bayesian probability distribution, and we calculate approximation function to find potential maxima. About algorithm a little.
Yes.
Firstly, we build a surrogate model that will help us to find the next step. So
surrogate model is chosen by using the Gaussian processes, which help us to surrogate model is found by regression, and this model models the true function, and it helps us to define its prior. Then by given the set of observations, we can use Bayes rule to obtain the posterior, and after that we can use an acquisition function, which is a function of the posterior probability to decide the next sample point.
And we do this with finding maximum of posterior function. And we do it till we reach a set limit.
When the function.
I want to rephrase so that everyone could understand just a few words. So actually, you can go back to the next slide. So to the next slide, yes. So the key idea of the Bayesian optimization approach in this algorithm is that even though we do not have any kind of information about the objective function or derivatives and so on and the shape of it, we using the Bayesian optimization approach, we kind of constructing the distribution, or we are kind of evaluating the shape of the objective function using the Bayesian updating approach. So the more points we evaluate, the more solutions we generate, the more precise our solution is. But the problem is, of course, that the computational complexity for this method is very big. So, but you will tell about this later. Thank you.
So the acquisition function, this function chooses the next query point as the one which has the highest probability of improvement over the current max. So you can see the two-dimensional example where green line is actually the acquisition function.
We try to find the highest probability of potential maxima.
In this animation, you can see the process of searching for the maxima of two-dimensional example. In the bottom of the picture, we can see the acquisition function, which helps us to choose the most the biggest probability of the next point in each step. I guess we can continue.
Tell about Stiblinsky-Tank function. It's also usually used for testing different optimization methods, and a few properties of this function. It has a number of minima multiple to dimensions, and we can always evaluate global minimum with formula you see there. Yes, there. Function and minima.
Here you can see the convergence graph of two-dimensional example. As you can see, it converges really fast. And on the next, in the right, we can see the Stiblinsky-Tank function visualization with minimum.
There pictured visible seal at global minimum. So there are computations.
Here you can see the evaluations.
And there is what if we increase dimensions to 20?
And as we can see, it does not converge normally. It finds some local minimum, I guess, and it doesn't go to zero convergence, I mean.
So I think that's all.
I think that's all, yeah.
Okay, thank you very much. So this kind of problem, all the methods that we are discussing today have. It is not a big problem. Yeah, but this method only works for a low dimension currently, but it is used not only in applied optimization, such operation research tasks, but also in some machine learning methods. And it is useful there. I think it's more useful there. For the operations research problem, it's not very convenient. But anyway, what you need to understand from this presentation, all of you, is that sometimes there are practical problems where you cannot really evaluate your objective function as many times as you want. For example, the ant colony optimization algorithm, there you can evaluate your objective function for 1,000, 10,000, 100,000 times, and you can think that it's not a big problem. But for example, the optimization problems related to chemistry or some biological, for example, you want to create an optimal drug. In order to create it, right now, people are using optimization algorithms to change the chemical, to simulate chemical reactions and to change this particles or whatever, to combine the best optimal drug. That is what is being done in the industry and in research as well. And there, of course, each evaluation is very expensive. Yeah, and if we want to do evaluation in the real world, that's very expensive. You want to do evaluation in the simulated environment, the one that you use is okay, yes. But if the real world, you need to a kind of a surrogate model. The surrogate model is what the Bayesian optimization algorithm uses. He uses some regression model to make the form of the real objective function, to approximate the objective function. And that's actually another direction. So if you have this a problem of a very expensive function evaluation, expensive in time or expensive in computation power, expensive in money and so on, then you can use surrogate models. But the problem with surrogate models is that they are not precise enough, and therefore you will have problem with that, so that you cannot sometimes get to the optimal point. That's it. Okay, thank you very much. The same question, have you implemented the code by yourself, or you used some open source solution? Прием.
Actually, we have found an open source solution.
Okay, no problem, because
yeah, can you hear me?
Yeah, it's not a problem. I did not have this kind of requirement. Okay, thank you very much.